So welcome everyone to this IFIS seminar. Today we have Ramon Aguado. He has visited the IFIS several times, so yes, he's a known visitor here. And he's expert on quantum transport in systems like quantum dot, quantum wire, on topological systems. Well, he's expert on many things already. He's, how to say, associate researcher or?
Yeah, senior researcher.
Senior research at the Instituto de Ciencia de Materiales de Madrid. And today he's going to explain more on quantum dots with superconductors, right? So yes, thank you for your visit.
Thank you, Rosa.
And for the seminar.
Yeah, of course. Thank you, Rosa, for the invitation. It's always a pleasure to come here back to Mallorca. As Rosa said, I've been here many times and I like it a lot. So thank you very much. So yeah, today I like to tell you about the role of this so-called Yu-Shiba-Rusinov subgap states in superconductors, in particular in hybrid devices fabricated by superconductor, semiconductor, nanowires, and in particular what happens when these systems contain quantum dots. And this is like the official title of the talk. Maybe a bit more provocative title would be what is the role of these Yu-Shiba-Rusinov states in so-called Majorana nanowires, these kind of hybrid systems which are supposed to have these Majorana excitations. All right, as an appetizer, let me remind you about this Majorana physics. Maybe some of you are not familiar about this idea. The idea is for this particular implementation of this nanowire implementation, the idea is to take some semiconducting nanowire which has strong spin-orbit coupling, like RASWA spin-orbit coupling. And if you take some external Zeeman field, which is perpendicular to a spin-orbit axis, you create helical bands in the semiconductor. Helical meaning bands in which spin and momentum are locked. And then if you put in contact this semiconductor with some standard superconductor, standard S-wave superconductor, the idea, this was demonstrated in a few papers, the idea is that you effectively create P-wave pairing. And this is a realization of this Kitaev model for one-dimensional P-wave superconductivity. And it is known since 20 years or so that this P-wave model contains a topological phase in which you have topological N modes. For this particular realization, this happens when the Zeeman field is larger than this critical value here, written in terms of this gap, induced superconducting gap in the system, and this is the chemical potential. So the idea is that for Zeeman fields larger than this critical value, you are going to enter a topological phase, a topological superconductor phase, which is characterized by topological N modes. In this case, these are Majorana zero modes. These are a very exotic excitation inside a superconductor, in this case, a topological superconductor, which is a zero energy excitation right in the middle of the gap of the superconductor. This is one point. The second point is that irrespective of the length of this system, you are going to have always two Majorana excitations, which together make a highly non-local fermion. So they can be very separated in distance, but still they are going to create a common non-local fermion. And the filling of this fermionic degree of freedom defines a two-level problem. And this is a non-local qubit. So this, together with the fact that these Majorana modes obey non-abelian statistics, they are not standard fermions, they actually obey non-abelian statistics, together defines this idea of topological quantum computing. So if you are interested, I have put here some references where you can find all the details about this topological quantum computing and these implementations of Majoranas. So this idea was simple enough. I mean, to take one nanowire, semiconducting nanowire, say indium arsenide nanowire, for instance, and put it in contact with a superconductor. That many labs in the world try to actually implement this idea, and this happened for the first time like 10 years ago or so in 2012. These are experiments from Delft, from Leo Kapenoffen's group, where here you see an image of the device. You have some indium antimonide nanowire, some superconductor. And the idea is that the presence of this state right in the middle of the superconductor, this zero energy state right in the middle of the gap of the superconductor, is going to appear as a peak, as a zero voltage peak, zero bias peak, when you study transport, conductance. In this case, this is a contour plot of DIDP, conductance as a function of voltage and magnetic field. And you see here that at zero magnetic field, you have the superconducting gap. And at some point, you start to see the zero bias peak that was interpreted in these first experiments as coming from Majoranas. And this is like another generation of devices, much cleaner devices. And these are experiments from Copenhagen, from Charlie Marcus's group, where you can see this very nice, very robust zero bias peak. And this is B field, is hidden here, but this is B field. This is very robust zero bias peak, which again was interpreted as a signature, a strong signature of one of these topological excitations in the semiconductor. All right, despite this amazing data, I mean, this is a very hard, very nice clean gap, and very hard, very robust zero bias anomaly. Very soon, right after these experiments, we started to have a discussion of whether these kind of peaks can be, unambiguously interpreted as coming from Majorana, or whether you can actually understand this in terms of Andreev subgap states in the superconductor, like in general, Andreev levels, or more specifically, if you want to focus on the physics of quantum impurities with spin, degrees of freedom, whether these are coming from Shiba states or other ways of creating subgap states. So this has been this ongoing discussion in the field for already a few years of whether these signatures come from Majoranas or Andreevs or Shibas. And if you are interested in this discussion, we have this review with some colleagues in which we give all the details about all this discussion, all the possible mechanisms that can give you this kind of subgap levels in these systems. And it's from Andreev to Majorana states in this hybrid superconductor semiconducting wires. All right, so as I said, I'm going to focus on the physics of Yu-Shiba-Rusinov levels, for short, Shiba levels. And these are subgap levels that appears in systems where you have quantum dot physics involved, all right? And the point I want to make is that, as I mentioned before, typically what you want to do is to study some transport configuration. You want to send some current across this device, and you want to measure conductance as a function of voltage. And typically what you do, in practice, what you do is you create some tunneling region here. And this is the brown here is the part of the nanowire which is covered by the superconductor, while green is the part which is uncovered, because you want to gate this short region here, you want to gate it in order to create some tunneling barrier, okay? You want to do tunneling spectroscopy, transport. And the point is, this is, for instance, this image for Yorgos Katsaros in Vienna. This is another example. This is in Copenhagen. You see, again, the green and the blue. Here, this is one of these new generation of devices called full shell nanowires. This is a semiconducting core. This is the green part, the indium arsenide core, which is epitaxially covered by a very thin layer of a superconductor, in this particular case, aluminum. And again, you see here in the image how you have the blue, you have the superconducting core, but there is some uncovered part, which is the one that you use as a tunneling region, all right? And the point I want to make is that in many of these cases, what you do is unintentionally, because you want to create a tunneling region, unintentionally, you create quantum dots. And you actually have to consider the physics of quantum dots in this kind of systems. All right. So the minimal model for studying a quantum dot, which is coupled to a superconductor, which is this segment of the nanowire, which is proximatized by the superconductor, the minimal model is this Anderson impurity model, the so-called superconducting Anderson impurity model, because this is an Anderson impurity which is now coupled to a superconductor. And some of you here, Rosa is an expert on this kind of problems. The idea is that you take a kind of minimal model for the quantum dot. You have some spinful level in the quantum dot, but now you consider this coupling to the superconductor. You have a gap, you have Cooper pairs, and you have this BCS-like density of states in the superconductor. And the point is that for odd occupation, when this quantum dot has odd occupation, this is a spinful quantum impurity. It's like a Kondo problem. But now this Kondo problem is modified by the fact that you are coupled to a superconductor instead of a metal, of a standard metal. So it's like the superconducting counterpart of a Kondo problem. Okay? And maybe you also want to consider the coupling to this normal lead that you use in this transport configuration. All right, so you have a spin coupled to a superconductor. Already at the classical level, this problem was well understood in the 60s, and this is actually the name comes from the three authors that studied this problem in the 60s, the Yu-Shiba-Rusinov, who demonstrated that still a classical spin coupled to some BCS bath, so BCS superconductor, has strong pair breaking character. It means that if I put a spin inside a superconductor, this spin couples to the electrons forming the Cooper pairs in the superconductor, and eventually you can break Cooper pairs because of this spin exchange with this impurity. Okay, you can break Cooper pairs. And this breaking of Cooper pairs is reflected in the appearance of subgap states, states that live below the gap of the superconductor. You can bind states in the superconductor by breaking Cooper pairs. So this is the cartoon. You have a spin here, which is exchange coupled to the Cooper pairs, to the electrons forming the Cooper pairs. This is parameterized by alpha. This is J times S, the spin. So you can have two possible configurations, the essentially free spin or weakly coupled spin to the superconductor, or if the exchange is large enough, you can actually bind singlets. You can break Cooper pairs and you can bind singlets between the impurity and these free spins now, and the spins coming from Cooper pairs. And these are actually the Yu-Shiba-Rusinov singlets. And the energy you gain in this process gives to the appearance of these kind of resonances inside the gap of the superconductor. And the position in energy of this resonance is given at this classical level, is this given by this expression in terms of alpha. And you see here that for alpha very small, near zero, this is essentially 1. So you are right in the gap of the superconductor. But as alpha approaches 1, this quantity goes to 0. So the position of this peak goes to 0, all right? And physically, what this means is that I start with a ground state, the standard BCS ground state plus the impurity. The first excitation is going to be this singlet, this Shiba singlet, and the energy separation between this ground state and this Shiba singlet is given by this energy here, omega naught, which is the position in energy of the subgap level, okay? As I increase alpha, eventually this distance, this energy goes to 0, as I said. The levels cross, there is a level crossing, which is a phase transition in the system. And after that, this red line is below the blue one. So this is my new ground state for a strong alpha, for a strong exchange, now the singlet is the ground state of the problem. So I completely changed the ground state of the superconductor. Okay? This is at the classical level. What we want to do now is to go quantum and to study the full quantum impurity problem. And this, as I said, this is an Anderson impurity problem. So again, this is the part describing the quantum impurity, like a standard Anderson model. You have some level, which is a spin degenerate. You have the U coming from the strong charging energy in the quantum dot. And now you want to couple this quantum dot, this Coulomb blockade quantum dot if you want, or quantum impurity Anderson model if you come from the other language. You want to couple it to this superconducting bath. And this is the part of the Hamiltonian describing the VCS superconductor. And this is the pairing, the VCS pairing in the superconductor. And these two systems are coupled together through this kind of tunneling term, coupling electrons in the bath and electrons in the quantum dot. And this is parameterized by this parameter, gamma S, which tells me about the coupling between the quantum dot and the superconductor. All right. So mathematically, I mean, I'm not going to give you details of the calculations, but mathematically, what we want to study is the position of the poles of a Green's function, okay? The position of the poles of a Green's function are going to give me these subgap states, right? And this I have to write in Nambu space because I need to keep track of both holes and electrons because I have superconducting correlations in my system. But at the end of the day, this is essentially a Green's function that is governed by some self-energy. The part of the Green's function coming from the coupling to the superconductor is written here. This is, again, this is in Nambu space. This is the electron part. This is the hole part. And this off diagonal tells me about these anomalous correlations that are induced by superconductivity. So one typical limit in this kind of systems is this so-called infinite gap limit. In this case, what you do is you assume that the gap of the superconductor is the largest energy of the problem. So essentially, you neglect all quasi-particles in the superconductor, right? The gap is infinite. I don't have quasi-particles in the superconductor. And this is equivalent to saying that I take the limit where this self-energy is static. I take the zero frequency limit of this self-energy, and I end up with this very simple form of the self-energy in which I have only this off-diagonal term coming from proximity effect multiplied by a constant. All right? Please.
Sorry, may I ask?
Please.
In the superconductor, you have electron hole symmetry.
Yes.
And in the dot, you don't have this electron hole symmetry.
Yes. When you do Nambu, when you write everything in Nambu space, you are going to have electron hole symmetry. Yes. The original quantum dot is just a standard model, but actually you can see here. When you plug this self-energy in this large gap limit into the quantum dot model, you end up with this kind of local pairing term in the quantum dot, and this already has this electron hole symmetry. Because the poles of this is here actually. You end up with this local pairing. You have integrated out the superconductor, if you wish, by taking this infinite gap limit. You end up with this local pairing term, and now you can diagonalize the problem exactly. You have the two possible spins. This is the doublet, or you have the VCS combinations of doubly occupied electrons in the dot or empty states, plus and minus, and these four states give you the electron hole symmetry that you wanted. This is plus minus in the quantum dot. So these two phases define this phase diagram in terms of parameters of the quantum dot problem. This is the level position of the quantum dot with respect to half filling. So at 0, I am in half filling in the quantum dot. So, and this is the coupling to the superconductor. So for very small couplings here near half filling, I am in this doublet phase. This is essentially a free spin, all right? The coupling to a superconductor is small, so I have a free spin. If the coupling is large enough, I enter this other phase where I have this kind of Bogoliubov-like or VCS-like superpositions of 0 and doubly occupied states, and this is a singlet. And these two boundaries, these two phases are separated by this analytical boundary, which is given here in terms of parameters of the quantum dot. So this is an exact phase diagram of the problem in the limit when I remove all quasi-particles from the superconductor. Okay, this is the infinite gap problem, infinite gap limit. All right, but in real life, of course, the gap is finite, and this superconductor contains quasi-particles. So I have to take into account the possibility that this electron now can be coupled to electrons, to quasi-particles in the superconductor, pretty much the same as I have in a Kondo problem. I can have Kondo exchange between this spin in the dot and this spin in the superconductor. So in the opposite limit, the previous limit was the large gap limit. Now in the opposite limit, when U, the Haber U, is much larger than the gap, this BCH singlet is much higher in energy. And actually the first singlet excitation is this kind of singlet, which is the Yu-Shiba-Rusinov singlet, but now in a quantum version. And this is essentially like a Kondo singlet, but in a superconductor, okay? So Shiba singlets are like Kondo singlets in a superconductor, okay? All right, so I had this boundary before separating singlets and doublets, and now if I introduce Kondo correlations want to screen this spin, right? So this boundary is going to be reduced because of Kondo-like processes screening this spin. And now the boundary is defined in terms of the Kondo temperature of the problem. And when the Kondo temperature is of the order of the gap, I'm going to have the new boundary. So for large Kondo temperatures, I'm going to have this Kondo-like Yu-Shiba-Rusinov singlets, while for a small Kondo temperature as compared to the gap, if the gap is large enough, I'm going to live in a doublet, okay? This is the phase diagram of the problem, which is no longer analytical. Now you have to do like tough numerics to obtain this boundary. But at the end of the day, it's about obtaining the Kondo temperature of this superconducting problem. All right, the point now is that if you now fix the coupling to the superconductor, this gamma S, this is the yellow line, if you now move the level position of the quantum dot, you can go from singlet to doublet to singlet. And this you can actually see in an experiment, and these are experimental, this is experimental data from Silvano Franceschi's group in Grenoble, and this is data taken by Eduardo Lee. This is a Nature Nano that we published a few years ago. I was involved in some theory with them. And essentially the idea is now you can excite this kind of Shiba excitations in the singlet, but you can put an electron here, which is reflected as a whole by having an Andreev reflection in this superconductor. You put a Cooper pair. So essentially you can measure excitations in DIDV, in transport, and you see these excitations in the system as peaks. This red line here, this is a contour plot of the derivative DIDV. This red line is essentially a peak in conductance, okay? So here, when you are in the singlet, you see this line. This is essentially the gap of the superconductor. This line lives near the gap. But as you start to change, this is a gate voltage that you put in the experiment that essentially is moving the level position of the dot. You start to see how these two lines, and these are the electron hole symmetric lines that you wanted, Llorens. These are the electron hole lines. They go to zero. They cross zero energy here. And now you enter into this loop here, which is essentially this phase here. This is the doublet, and you are back to the singlet. Here the line cannot be seen, but you are back in the singlet. So these kind of loops or eyes in DIDV are a signature of this doublet phase in the quantum dot coupled to the superconductor. All right, now you have to remember that these peaks are actually excitations on top of the ground state, okay? So if I am in a singlet, my peak is a doublet excitation, okay? Meaning that if I put a magnetic field in a singlet ground state, my excitation, which is a doublet, is going to split due to Zeeman splitting. The line is going to split. But on the contrary, if my ground state, if I am inside the doublet, the line that I measure is an excitation line corresponding to a singlet. And this singlet is not going to split under magnetic field. Okay. So this is corroborated by experiments. This is the plot that I just showed you before. If we put a finite magnetic field, you see that inside this doublet, the lines do not split. While if you are in the singlet, you clearly see this Zeeman splitting of the lines. So this means that the Zeeman splitting in this system is gate dependent and it's extremely nonlinear. It's not the standard Zeeman splitting that you expect, right? And there is full agreement with theory. I mean, I'm not going to give you details about the theory, but there is full agreement with theory about this kind of exotic dependence of the Zeeman splitting in this system. This is as a function of gate. You can now study this kind of splitting as a function of magnetic field. So starting here, you have these 4 lines, this split line at positive bias, a split line at negative bias. So you have 4 lines, right? 1, 2, 3, 4. But now you keep increasing magnetic field, and eventually this split line is going to cross 0 energy again, because you fully polarize the impurity. You fully polarize the excitation. So you are back to a spin ground state. So you are back to 2 lines instead of 4. So you expect to see in the experiment these 4 lines becoming 2 and how they cross 0 energy. And now you have to remember that these lines in the experiment are actually kind of resonances in the IDB that have some finite width. So what you expect to see is some lines which are broadened, and eventually they're going to cross 0 energy or 0 voltage. But because there is some finite broadening, you are going to see some kind of sticking 0 bias peaks in a range of Zeeman fields of the order of the broadening of the line. All right. And this is indeed demonstrated in the experiment. This is published in this paper a few years ago, where you clearly see how 4 lines become 2 lines after this crossing. This bending that you see here is because the superconducting gap is also closing here. But the important point is that there is a clear induced quantum phase transition between a singlet and a doublet. And here, this 0 bias peak, if you plot this contour plot against magnetic field, you see very clearly 0 bias anomalies that come from this Zeeman splitting of Shiba levels in a quantum dot, nothing to do with Majoranas. Okay, nothing to do with Majoranas. All right, so this was for these kind of old experiments. Let me now change gears to this novel geometry that I already mentioned in the introduction. This is the full shell nanowire geometry, where you have this semiconducting core. This is the green part. And you have this full shell, which is fully wrapping the semiconductor. Okay, this is like a cannelloni, you know, you have the semiconductor inside the cannelloni. And now you put a magnetic field. So because these wires have a finite area, you put a finite flux inside this superconducting loop, right? So now you have to take into account the fact that because this is a superconducting shell, if you put a flux across this area, you are going to induce supercurrents around this flux. Essentially, you are creating a vortex, like in a superconductor, right? You are creating a vortex in this direction. So you have to take into account this supercurrent flow around the vortex that wants to screen the magnetic field that you are putting here. So this gives rise to this concept of Fluxoid quantization, where together with the external flux that you have, the contribution of this supercurrent, which is circulating around this circle here, both together have to be quantized in units of the flux quantum, superconducting flux quantum. So if you do the math, which is trivial, you end up with this expression. This is the superconducting velocity, which is written here in terms of an integer number in units of this external flux over the flux quantum. So if you plot now the velocity square, which is essentially the kinetic energy of the system, what you see for a given integer 0, for instance, this is this parabolic shape. This is v squared. This is this parabolic shape in terms of n, or sorry, in terms of flux. But eventually the system, instead of growing in energy, wants to go to the next integer because it minimizes the energy, right? So the velocity has this peculiar behavior as a function of external flux, and this modulation of supercurrent flow is called Lidl-Parks effect. And this is well known in the superconducting community. This is actually in Tingham's book, in chapter 4. You can actually, I believe I took these figures from Tingham's book. Maybe I'm not sure. But anyway, you see this nice modulation, and this modulation of these Lidl-Parks modulations leads to modulations of the supercurrent. And here are experiments from Copenhagen, from Charlie Marcus' group, where you see this is a current bias measurement of essentially this is the supercurrent in the system, and you see very nicely these Lidl-Parks oscillations of the supercurrent across this nanowire. This is like weak modulation, but the interesting point occurs for this other plot, in which, depending on the geometry of the shell, you enter this so-called fully destructive Lidl-Parks effect, in which you go from here, black is supercurrent, you see here there is black, but eventually if I keep increasing magnetic field or flux, I completely destroy superconductivity. Here I'm in the so-called fully destructive Lidl-Parks effect, where I completely quench superconductivity. But now if I keep increasing the magnetic flux, eventually I enter into in the first lobe of the Lidl-Parks effect, and superconductivity is restored. So it's amazing because you are tuning superconductivity on and off by an external magnetic flux in a very controlled manner. And the dashed line is theory. The contour plot in color is experiment. So the agreement is amazing with these experiments. All right, so these are very nice systems in which you have a very precise control on superconductivity. And the theoretical prediction, which is in this paper, in this science paper that these authors published like 2 years ago or so, there are some theories here, Roman Luchin, Carsten Fleischberg, Leonid Gladden. Well, you know some of them for sure. So the theory prediction says that because I have this precise control on superconductivity, under the right parameter regime, I can find regions where I enter a topological phase with Majoranas here in the first lobe in a very controlled manner. So there is a very precise theoretical prediction which says in the first lobe, if I am in the right regime, I should see this kind of zero bias peak coming from Majoranas. This is the theory, and this is the experiment in which this is the first flux, first lobe, in which you see again very clearly this robust zero bias anomaly that for these experiments was interpreted as coming from Majoranas, as coming from a topological state modulated by this Lidl-Parks effect. All right, so together with our friends in Vienna, Yorgos, Katsaros, Marco, and others, we wanted to do a kind of more systematic study of this kind of full shell nanowires. They did the experiments, we did the theory. And actually, these are the same wires, Peter Grostrup here, you see the same name. These are the very same wires that Peter Grostrup is growing in Copenhagen. So what Marco and Yorgos and the rest did was to study very carefully the role of this tunneling region, because we knew from the previous papers that these tunneling regions can be important for this quantum dot physics. So they did very systematic experiments in which you control very carefully the length of this tunneling region, and you study what happens in transport when you change the length of this tunneling region, okay? The conclusion is that for this green part, for the tunneling region part, when the length is, let's say, below 200 nanometers or so, typically you always see standard tunneling barriers. So you always see, this is conductance as a function of backgate. This is essentially, for the experts in the audience, this is essentially BTK theory, right? So you have a gap here, you are in the tunneling limit, you start to reduce the backgate, you start to have enhanced Andreev conductance, which is Andreev enhanced tunneling. This is BTK theory, standard tunneling junction. If you do the same with magnetic field, you have a very nice gap, zero lobe, this very nice destruction, reopening of the superconducting gap, little Parks modulation. But the point we want to make here is that there are no subgap states in the system, never. You don't see any subgap state here, never. When you are below this length, when you are in the true, let's say in the true tunneling limit, when you want to perform tunneling spectroscopy, you never see subgap states. On the contrary, when the length of this tunneling region is above 200, 250 nanometers or so, you start to see very clearly quantum dot behavior in the system. So this is for a given sample here, in which you have to compare this conductance plot versus gate with this other conductance plot, where you clearly see these loops that I was talking about before. This is clearly quantum dot physics, quantum dot loops. This is a doublet, this is a singlet. They do what we expect them to do. When you are in a doublet, you see this kind of loop. They are split under Zeeman, the same things that I was discussing before. All right, but now we have this little Parks modulation of superconductivity. So the effect of a magnetic field is much more involved than just the Zeeman, right? Because we have the flux in the system. So you have to take into account this little Parks effect, this modulation of the superconductivity due to little Parks. So we did theory in this limit, in the limit when we are in the doublet. And if you are at half filling, when you are really in the doublet state, essentially you are in the spinful limit, in which you can treat the impurity at mean field. And you do the full theory at mean field, and you can actually obtain analytical expressions for this kind of Yu-Shiba states, Yu-Shiba singlets, which are just modified by the little Parks effect in the gap of the superconductor. And now you can compare the lines, the experimental lines, which are this color in the contour plot, with the dashed line, which is the analytical prediction of this equation, and you see that the agreement is almost perfect. So there is this little Parks modulation of the Yu-Shiba levels, and this is indeed a Yu-Shiba singlet, which is modulated by little Parks effect. And all the details can be found in this paper that we published in Science 1 year ago or so. All right, this was for the doublet. For the singlet, we can do the same. We can study the spin splitting of the singlets. This is against gate, and this is essentially the same I showed you before. But now, if we study how these singlets evolve under magnetic field together with little Parks, we see this kind of very weird Zeeman splitting of the levels. Here, essentially, you don't see anything. So the levels are flat. Here you have this kind of highly nonlinear splitting, which is kind of skewed towards the right. And here, maybe you see some zero bias peak. And to make a long story short, is the moral of the story is that if you put all these ingredients in an Anderson model, you take into account Zeeman, little Parks, and everything, you can find situations where, and these are calculations, energy calculations by Rock, by our collaborator Rock Thitko, where you see here Rock is changing the G factor, and you see how these levels are pretty flat, and how by increasing the G factor from top to bottom, you start to see this kind of splitting, but in a kind of very non-trivial manner, right? So for instance, here, if you put some broadening, probably this is, or maybe this is pretty much this situation that you encounter in the experiment. Very similar results can be also found at the Hartree-Fock level. Of course, the agreement is not perfect, but essentially the qualitative behavior is the same. But here you still see levels inside the zero globe. So this is clearly coming from subgap levels. But there are situations in the experiment where essentially you see, you don't see anything inside the gap of the zeroth lobe, and out of the blue, you start to see kind of zero bias peaks in the zeroth lobe, sorry, in the first lobe, here or here. You start to see zero bias anomalies, while here you see nothing. And this is similar to the features that were found in the previous experiment by the Copenhagen group. We are not claiming that these features are the same. We are just claiming that there is this alternative explanation for the experiments. Indeed, you can have situations for large coupling between the quantum dot and the superconductor in which you can have subgap states essentially lurking near the gap of the superconductor, and this bright line could be very easily this kind of bright line in the experiment. And then after the first destructive regime, you start to see this kind of zero bias anomaly, which maybe has some little broadening here. You see this pretty nice agreement. This is Hartree-Fock, this is NRG. And depending on parameters, you can find this kind of configurations. And the point is that this phase diagram that I showed you before, this dome, now is modulated by both Zeeman and the flux, this little Parks effect. So the gap is modulated by the flux. So you can actually go in and on these phases by modulating with the flux, because you move the boundary of the of the phase transition. All right, this was this paper where we demonstrated unambiguously that at least for the experiments in Vienna in Jorgos' group, all the data can be explained in terms of quantum dot. This has nothing to do with Majoranas. We are not claiming that Copenhagen is the same. We are just saying that our data is consistent, fully consistent with quantum dots. And now there is, well, this is just to illustrate this kind of non-trivial splittings. And there is yet another non-trivial effect coming from this cylindrical geometry, and it's the fact that you have to take into account the winding of the superconducting phase around the cell. So apart from this little Parks modulation of the order parameter, you need to take into account the fact that you, as I said before, you are creating like a vortex in the superconductor. So if you take into account this winding of the superconducting proximity effect, now you have to take into account the fact that your quantum dot, depending on the position of the quantum dot with respect to this circle, to this winding, this polar angle, if you wish, and here is the cross section, depending on the distance, the tunneling between the dot and the ring, the superconducting ring, depends on this polar coordinate, okay? Because you have this vortex, this vorticity of the proximity effect around the shell. So essentially, you have to consider this kind of integrals where you integrate over polar angles this coupling of the superconductor of the quantum dot. And what we found is that when the dot is right in the middle here in this cross section, essentially, this is what we call symmetric configuration. Essentially, when you integrate out this angle, this polar angle, essentially this contribution cancels out because you do a full integral over the circle. And essentially the proximity self-energy, which is the same, I told you before for the large gap limit, now is the same self-energy as we had before, but now you have to notice this Kronecker delta here. So if I am in the zeroth lobe, I have the standard off diagonal coming from the proximity effect, but from the first lobe and higher lobes, this contribution disappear. Essentially the proximity effect is integrated out because I have to take these integrals, okay? I integrate out the contribution from the superconductor. So already at this simple level, you can see that the position of the pole is strongly renormalized because I have this off diagonal going to zero, is strongly renormalized by the coupling to the superconductor. So for large coupling, the position of the level is going to go to zero, towards zero in this case. And this is indeed confirmed by numerics. These are calculations by Samuel, doing again mean field. And you have to compare now this asymmetric coupling, asymmetric dot, which is essentially the standard Anderson model, with this other situation where I have this suppression of proximity effect due to this symmetry. And again, you can have zero bias anomalies, which again are due to this geometry of the shell, nothing to do with Majoranas. Okay, this is rather related to vortex physics. In this case, vorticity coming from these cylindrical coordinates. All right, in the remaining 10 minutes or so, let me change gears a bit and tell you about this kind of physics, but in a different context, in the context of superconducting qubits. So before I was describing how the presence of quantum dots is somehow negative in the sense that, you know, all, well, not all, but many of these Majorana claims maybe are actually understood in terms of quantum dot physics. And now what we want to do is to actually use this kind of Shiba excitations in a quantum dot in superconducting qubits, right? So I guess some of you know about superconducting qubits, or maybe all of you know about superconducting qubits. The idea is simple. You just take some Josephson junction where you have two superconductors. One of them is a superconducting island, which has finite charging energy, like a quantum dot. But in this case, this is a quantum dot for Cooper pairs. I have to pay charging energy for Cooper pairs. And this is described here by this term, which is quadratic in the number of Cooper pairs in the island. This is the charging energy. And this is the standard Josephson term coming from the coupling between these two superconductors. This cos phi EJ is the Josephson coupling. And now, because this is a full quantum problem, the number of Cooper pairs and the phase difference are conjugate variables and quantum variables. So essentially, the number is the derivative of the phase, pretty much as position and momentum in standard quantum mechanics. So I need to solve this problem fully quantum mechanically. So if I am in the limit when charging energy is much larger or of the order of the Josephson coupling, what I have is this, as a function of gate, what I have is this kind of parabolic dispersion. So each of these parabolas here, this parabola, this parabola, this parabola, correspond to one extra Cooper pair in the island. So this is, say, 0, 1, 2, 3 Cooper pairs in the island. This is Coulomb blockade of Cooper pairs. So every time two of these parabolas cross, they differ by one Cooper pair. They are hybridized due to the Josephson effect, because the Josephson effect is putting Cooper pairs in and out the island, right? So these crossings here become avoided crossings. And actually, this two-level system is the system that I used to create a qubit. And this was actually the first realization of a qubit, of a superconducting qubit. This is the so-called Cooper pair box. This was experimentally demonstrated back in '98, I believe, in Nakamura's paper. This is the first realization of a superconducting qubit. But the point here is that the parameter that you change is this gate. Here, there is a strong dispersion against gate, meaning that if I have charge fluctuations in the island, which you are going to have in a real circuit, this curvature is going to know about these fluctuations. So this induces a lot of noise in the system, meaning a lot of decoherence in the qubit. So a novel design was proposed in this paper. I hope you can see it here on top. This is Koch et al. In 2007, where they propose to go to the opposite regime, to the limit where the EC over EJ is very small, where the Josephson coupling wins instead of the charging energy. In this case, you go from this parabolic shape to this other regime in which you have essentially flat levels. These are flat levels against charge fluctuation. So they don't disperse against charge. So they don't care about noise in the charge of the circuit. You essentially have a harmonic oscillator, and this is the frequency of this transmon called transmon qubit. The frequency of the transmon is given by essentially the plasma frequency of this harmonic oscillator, but it's still the fact that instead of a harmonic oscillator, instead of phi squared here, you have a cos phi, you have a Josephson junction. You have this small so-called Josephson inductance, meaning that you have weak nonlinearities in the system. So this is not a true quantum harmonic oscillator. You have a small anharmonicity. You know, you have deviations from pure parabolic shape. This is the green line. The red line is the cosine. So you have deviations from parabolic shape, which give you a small anharmonicity. And this is good because this allows me to address, for instance, by microwave, this transition without coupling to the other levels. If you have a pure harmonic oscillator, you cannot create a qubit because you have many levels that are coupled together. So this was the transmon, and this was a really good idea. And actually, this is the basics of all these famous quantum computers. The Google quantum computer, the IBM, all these computers have transmons inside. All right, so the idea is to go beyond the transmon and being able to tune the transmon fully electrically by gate voltages. So we want to replace the tunnel junction here by some SNS junction, which contains Andreev levels. Before, this was a tunnel junction where the macroscopic degrees of freedom of the junction are not relevant. This is essentially a tunnel junction back in the 50s or something. But now we want to make use of Andreev levels inside a Josephson junction. Already in the simplest case for this single channel limit, when you have this famous expression for Andreev levels in a single channel, you can tune the position of the Andreev levels by tuning the transmission of this single channel. And this you are going to do with the gate voltage, ideally. So you can go from this kind of situations, which some of you are very familiar with. Rosa knows a lot about this, where you are in a transparent regime, you have this kind of crossings near pi phase, and your current phase relationship is going to be a sawtooth, right? This sawtooth current phase relationship here, when tau equals 1. While if I put some finite transmission across the single channel, if the transmission is small enough, I recover the tunnel-like, you know, sine phi expression that you have in a tunnel junction, right? This is already with single channel junction. The idea is if I have an SNS junction with some semiconducting material, like for instance, a nanowire, I can tune both the transmission of the system and maybe also the number of channels. Now I can have many channels in the junction that I can tune with a gate. So this led to the concept of gate tunable transmon, also known as gatemon. And this was demonstrated in 2015 by these two groups, Delft and Copenhagen. And here, I'm not sure if you can see it, but this is again, this is an indium arsenide nanowire Josephson junction that you can tune the gate here in such a way that you can tune the Josephson potential, and you put all the Josephson geometry inside an island, inside a microwave cavity. You have all this circuit QED stuff that people in superconducting qubits do. And essentially what they were able to prove is that the frequency of this qubit can be modulated by this gate. This is the frequency of the qubit. This blue line, this is the fixed frequency of the resonator. Near these crossings here, you actually see strong hybridization between the resonator and the qubit, demonstrating a strong coupling between this transmon, which in this case is a gatemon, it's a gate tunable transmon with a nanowire, and the resonator. So this is the first demonstration of a superconducting qubit based on semiconductors instead of superconductors. All right, now we wanted to explore the same idea, but now using quantum dots. And this is a very, very fruitful collaboration with our friends in Delft, Bernard Van Heck, Angela Koh, Leo, and co-workers, and very nice experiments by Arno Vargebos and Marta Pita-Vidal, who is actually a Spanish student there in Delft. So the idea is to replace this Josephson junction now by one of these quantum dot Josephson junctions, and see whether we can control the physics of these Yu-Shiba levels and how they affect the properties of this superconducting qubit. So we have a quantum dot model. We use a split junction geometry. So we have like a squid We have a reference Josephson junction here. We have external flux, and we are going to tune all the parameters of the Anderson impurity model, both theoretically and experimentally. This is the experimental plot. This is the nanowire here. Here you have the quantum dot. This is the reference junction here. This is the closed loop that we are going to use to induce this flux here to essentially to change the phase across the quantum dot to have phase tuning. And this whole circuit is coupled to this floating island, which eventually is coupled to the rest of the microwave circuit. So they fabricated this superconducting qubit with this quantum dot in the middle, okay? So the cartoon picture that we have in mind is that my superconducting qubit now has the charging energy part, and now I have a modified Josephson potential because together with the reference junction, which is a standard cos phi Josephson potential, I have the quantum dot, the contribution of the quantum dot to the Josephson potential. And this can be, as I've been discussing along the talk, this can be either in a singlet or in a doublet configuration, depending on all this Yu-Shiba physics. And essentially the idea is that if I am in a singlet, my Josephson energy is going to have a minimum at zero phase, and this is a zero junction. We've been discussing about this before lunch. While if I am in a doublet, the Josephson potential is going to be in so-called a pi phase, because the minimum is going to be a pi now. So if I add the reference junction, the expectation is that two configurations of the quantum dots are going to give two different Josephson potentials, depending on whether I am in a singlet or in a doublet, meaning that the transition of the qubit should know about whether I am in a singlet or in a doublet. Okay, this is the idea of the experiment. And again, if we do some calculations, this is again mean field. You can be either in doublet or in singlet, and depending on the phase, again, if you are in a singlet, the minimum is this is against phase difference in the superconductor. This is the minimum is at zero, and I have a maximum at phase pi. While if I am in a pi junction regime, the minimum is going to be a pi. And actually, we can have this pi prime that we were discussing before. These pi prime configurations where I am in the middle between 0 and pi, this kind of intermediate configurations when I have local minima near pi, but the global minimum is still at 0, or I can have 0 primes also. All right, anyway, this is mean field. What we want to do, we really want to do, again, the full Kondo-like calculations, taking into account all kinds of contributions in the problem. So again, Rock did a very nice job in doing energy calculations for this superconducting Josephson junction in such a way that I can obtain the Josephson potential of my quantum dot. But now I have to work a bit more because I want to include this quantum dot Josephson potential inside my superconducting qubit. And the trick we use is to decompose this energy Josephson potential containing Kondo and everything into Fourier components. We have the cosine and the sine. And the point is that we want to decompose these cosines and these sines in terms of exponentials, because as I told you before, the phase and the number operator are conjugates, are quantum conjugates. So essentially the exponential of the phase puts Cooper pairs in and out. This is kind of a ladder operator for this number. So if I put an n here, this started from n, I put n, small n here, using this kind of ladder operators, which are coming from quantum optics and so on. So essentially, I can write this Josephson potential in terms of these ladder operators in the charge basis of the Cooper pair, and I end up with this kind of tie binding model. This is the diagonal part coming from the charging energy, and these off diagonals are weighted by these Fourier components, which are defined here as integrals of the Josephson potential that we obtain with energy. Okay, you follow me? So we now solve again a new problem of the superconducting qubit using this tie binding model, but now plugging into the tie binding these Fourier coefficients that we obtained from the quantum dot. So we solved the superconducting qubit model, fully taking into account all these Kondo, Shiba, and all these things. All right? We obtain the frequencies of the problem, and we can obtain the transition frequencies of the problem. And to make a long story short, essentially what we see is that inside the doublet loop, my frequency, this is the transmon frequency, the frequency goes below the reference frequency here, and the width is actually the calculation of the matrix element of this qubit transition. While if I put a phase pi, now I promote this doublet because I am in a pi phase, and now the line is above the reference. So below means doublet at 0 flux, above means pi junction, and the other way around. And this is actually very nicely seen in the experiment. This is experimental data. You see here versus plunger gate, and this is the resonator frequency. And you see here, for instance, around this region, how we see very clearly these sharp drops in the qubit frequency coming from the quantum dot. And this is for 0 phase. Now, the drop goes below the reference, but at pi phase, this behavior is reversed in very good agreement with the theory. And the same is seen in two-tone spectroscopy, where we can actually measure the transmon frequency. Again, this goes below, this goes above the reference. So if we define whether this line is below or above the reference, we can translate all these transitions into colors in a contour plot. This is red, means that my line is above, so I am in a pi junction, or blue means that I am below, so I am in a zero junction. So by mapping the experimentally obtained transition frequency of the qubit to this color versus plunger gate and phase, I can obtain this phase diagram when red goes to blue, blue goes to red, and so on and so forth. And this oscillatory behavior, these are the boundaries between singlets and doublets, or 0 and pi phases, that you can measure directly with a transmon qubit, which is pretty cool, I think. And you see here the agreement with theory is really good, actually. You actually see all these boundaries in very good agreement with theory. And you can fix the frequency now and study the same against plunger gate. And this is the doublet that I showed you in the beginning of the talk, the doublet boundary, the singlet against the level position of the quantum dot. This is theory, this is the experiment. And again, this color is obtained for transitions frequencies of a qubit. So there are, thousands of points inside this contour plot. And you can map very nicely this boundary of the singlet doublet transitions directly with a superconducting qubit. And something even more interesting, I think, is the fact that when we put an extra pi phase in the system, this was known in theory for 20 years or so. And again, we were discussing before with Rosa, for a pi junction, because you have essentially a two-channel Kondo problem, when you put a phase pi, you essentially have destructive interference between the two channels, right? And you have an over-screen Kondo problem. So this doublet becomes promoted, and near half filling, the doublet is always the ground state of the problem when you put a pi phase. And this was predicted in theory by some Japanese papers in, I don't know, 90 something, a lot of years ago. But this is, as far as I know, the first experimental demonstration. This is experimental data. The first experimental demonstration that when you go from 0 to pi, indeed, you have this over-screen Kondo phase diagram of the quantum impurity, which is very cool, I think. Anyway, so this is all the details. I forgot to mention, all the details are here in this archive paper, and this is going to appear in PRX Quantum very soon. So this is the last slide. We are able to fully map the phase diagram of this quantum impurity, and actually they can perform time-resolved spectroscopy of this microwave signal, and they see this kind of random telegraph noise between two states in the microwave signal, and we can actually interpret these two states in the microwave coming from the two possible parities in the quantum dot. And by doing a Fourier analysis of this random telegraph signal as a function of time, we can do this kind of analysis, and we can extract actually the relaxation times of my qubit, of my spin qubit, if you wish. And the good news is that the lifetime of the ground state is always of the order of several milliseconds. And this always exceeds the lifetime of the excited state at least by 1 order of magnitude. So for instance, here inside this doublet loop, this is the relaxation times of my system. You see here that the lifetime of the doublet phase is 6 milliseconds, while the lifetime of the singlet is much, much smaller. So this means that we essentially can use this quantum dot to create an Andreev qubit, a spin qubit inside a superconductor. And the fact that I'm using a quantum dot, the fact that I have a strong charging energy in the Yu-Shiba regime, helps me because I have very long parity lifetimes. So we believe this is a very strong result, and we are working towards demonstrating Andreev qubits, pretty much the same ideas that were demonstrated in Yale, in Michel Deboré group, but in their case, they only had the Andreev qubit with just a standard Andreev level. In our case, because we have the quantum dot, we believe that our lifetimes and our qubit is going to be much better. And with this, I finish. This is, well, the take-home message is that Yu-Shiba-Rusinov physics in this kind of systems, I think is fun. I mean, there are still a lot of things to do. We thought a few years ago that maybe we understood everything, but I think this is not the case. I mean, there are many things still to understand in this kind of systems, in particular in the context of these hybrid semiconducting wires. And let me put a long list of collaborators along the years in these kind of problems, including Rosa here, a lot of people in Madrid, Delft, Vienna, Rock in Ljubljana, Grenoble, Copenhagen, and so on, Pittsburgh. Okay, and thank you for the attention. Thank you, Rosa.
So now it's the time of questions. I don't know if people. So I repeat again. Thank you very much for this nice talk. It was very nice. So now maybe there are people that want to make questions on the online audience. I don't know if it is the case. Maybe you can, Hannah, you can say something. Maybe no. Okay. Seems that there are no questions from the online audience. I don't know if here in the presential mode there are questions. No. Okay, if not, maybe I can ask you some questions. One is how you can include this little Park effect on the level of the Hamiltonian?
Yeah, this is a...
It's a technical issue.
Well, there are two ways of doing this. Here, well, maybe here. So you can do this by putting the flux modulation of the gap that you get from little Park's theory, and this you can do, for instance, doing Ginzburg-Landau. So you have to do a Ginzburg-Landau theory for this gap and how it evolves as a function of flux. And once you have this, you plug this flux dependence of the gap inside the Anderson model. But this is known, this dependence. Well, yes, at the level of Ginzburg-Landau, if you are interested in the supplemental of this paper that we published in Science, we have all the details of how to put the little parks here. Or if you want to be more sophisticated, you can go to this kind of description. You put the flux, the fluxoid, the winding of the superconducting phase, and you can actually keep track of all the phases in the model, and you can do a full microscopic analysis of the problem. This you can do also. It's in the supplemental of this paper.
Okay. So here, since you have this slide here your nanowire is a hexagon, right?
Well,
So
in real life, it's
or-
an hexagon, but in our calculations, we consider that it's a circle.
Circle.
But it's not that relevant, I think.
It's not relevant.
I mean, some of the angular symmetries are slightly different. So, of course, you have to write. I mean, I didn't want to enter into technical details here, but all the details are here. But if you, what we do in the paper is that you write an Anderson model, and you couple this Anderson model to a tie binding chain, and this tie binding chain knows about this geometry. You have to take into account all the angular momenta, or the states, or the symmetries of the problem, and then you put the winding of the phase, and it's quite involved. I mean, you really have to take into account this kind of a multi-band problem instead. I mean, it's an one-dimensional in practice, but because you have this angular geometry, you have to take into account all these angular momenta. This is like for the simplest case. I mean, I didn't want to enter, but there's a huge, huge supplemental in the paper doing all the possible calculations. But yeah, to make a long story short, yes, you can include the leader parts from the very beginning.
In the experimental results that you showed before, you here, I think, yes, this one. So you mentioned that you can see these lines, right? These lines there. When the length of the junction is more than 200,
250. Yes.
And there is a way to know that this is like that. I mean, why is not 100 or?
Well, this is a good question, and we actually had a lot of discussions about this, and the answer is we don't know. We don't know, because you have this region here which is unexposed to the superconductor. So when you gate this, you are creating some kind of electrostatic landscape, and somehow when this electrostatic landscape, which should be of the order of the maybe some Thomas Fermi length or something, when this is short enough, maybe you create a quantum dot, I don't know, but probably it's so small that the levels live very high in energy, so you don't see these levels. This is maybe the explanation, but we really don't know. I mean, you would need to do, if you really wanted to know in practice, you will need to do a full, three-dimensional electrostatic calculation of this system with this boundary condition of the superconductor, which is like a metal, and then you have the gate, and to really see the electrostatic profile of this system, and whether eventually you create some quantum dots, some confining region in the system. So it seems that experimentally, this is kind of the number that they get, around 200, 250, but we really don't know, because we don't have an electrostatic model, for a realistic model for this.
But this doesn't depend on the length of the nanowire.
No.
So
it's clear that you can really identify these quantum dot features as soon, and this is like a very strong claim. I mean, if this length is below 200, you never see subgap states.
That's...
While when you are above, you always see quantum dot states, at least in Vienna. This is what I can say. If you discuss with Charlie, they will tell you that maybe I have to be very fair. If you discuss with Charlie, and we have discussed a lot with them actually, with Sole Vaitiekenas and with Charlie, they said that their fabrication method is slightly different. So it is true that the wires grown by Peter are the same, but the fabrication is performed in different labs. So maybe the way you fabricate this junction somehow creates more quantum dots using this method or the other, but they really don't know. They really don't know. But they were really open. I mean, we discussed a lot with them to see what is going on. I mean, to try to understand this.
Is there a difference with the peak height?
In this discussion, is there a difference in the Majorana case? The peak height in the IDB is 2e²/8.
Yes, this is a very good question.
Here it looks to be smaller, no?
Yeah, this is a very good question. So Of course, you know about this discussion about this quantized conductance peak, this retraction from Leo's group, Sergey from insisting a lot about this conductance quantization and so on. So the short answer is that you can fine tune situations where the peaks are close to 2e square of range, and they have these kind of peaks, but not always. So you can find,
you have to make a selection.
Right. So you can find situations, you know, when the coupling is strong enough, you can have very good conductance and you can be close to 2e square of range, but you can be below, like here, or above, you know. But this is like fine tuning. But if the levels, I mean, I didn't enter this discussion here. It's in this review paper. If the levels, instead of being related to Shiba states, if they are coming from a smooth confinement, if they are coming from the fact that you can create a smooth potential confinement, then you may create zero modes, which are still topologically trivial, but they actually give you exactly 2e square of range. And this is not fine tuning. And this is related to non-Hermitian topology. I'm not sure if you have followed this literature of non-Hermitian topology. So you can actually relate these Andreev levels in an open junction to non-Hermitian topology, exceptional points, bifurcations. I don't know if you're familiar with this. And there the conductance is 2e square of range. It's kind of robust.
Okay, so thank you. No more questions. So I think that we can stop here. We have many questions, but we can just ask you in private.
Very good.
Okay, so thank you very much.
Thank you again, Rosa. Thank you.